On 4.2, the quantum model of an atom. So we're going to talk about electrons again. Okay, we're not done with them. This entire chapter is based on electrons. So we'll discuss electrons and their wave-like properties, how we cannot determine the location of an electron based on velocity or position. You just can't. Talk about orbitals and then quantum numbers. So this is going to get kind of weird here. So Bohr's model, going back to Bohr's model of the hydrogen, contradicts some common sense, and these are the common sense questions. Why did hydrogen's electron exist around the nucleus only in certain allowed orbits with definite energies? What did we call those definite energies? Anyone remember? I believe it was called...
Photon.
Yeah, photon or quanta. Was a quanta a vocab term? Okay.
Yeah.
Why couldn't the electron exist in a limitless number of orbits with slightly different energies? Like, why can't you be on half a rung? So, yeah, some common sense here. So, to explain why atomic energy states are quantized, we had to change our views about the electron. So, here we go. So, first question here. Could electrons have dual wave particle properties like light? Yes. Yes, they can. So, Louis de Broglie, we'll say Broglie, all right, compared the behavior of electrons in Bohr's model, which he had theorized that each orbit had a quantity or it was quantized for a certain amount of energy, to known behavior of waves. So any wave combined in a space can have certain frequencies. Frequencies, how many waves are passing through a point in a certain time frame. Electrons are confined to a space around the nucleus and only at a certain frequency. And so we go back to Planck's equation, the energy of whatever the heck you're looking at equals h, which is that constant, times the frequency. And it helped us correspond to specific energies. Basically, if you imagine this as the nucleus of an atom, and these electrons, they're orbiting the nucleus in a quantized energy, but they're also behaving like waves. Can I move on?
Yes, miss.
Okay. So there were some other investigations that demonstrated that, yes, electrons do have wave-like properties. First off, diffraction. The bending of a wave as it goes around the edge of an object or through a small little pinhole or opening. So I'm sure you've seen this with flashlights. You turn on the flashlight and you see like rings going on here. Okay, that's diffraction. It's going through a small little opening, and you can kind of see that these are, like, you see the first ring. Actually, I would call this a ring. And then there's a ring here, and there's a ring over here. So it's very similar to, I'm just going to jump back and then I'll jump forward, this diagram right here. Okay. All right. Another property we found with these electrons, interference. When waves overlap, as a result, energy can be reduced in some areas and increased in others. So it's kind of like, I don't know if we ever did this in earth science. I had you as earth science kids, right?
Yeah.
We took slinkies on the ground.
Oh, yeah.
Yeah, we send waves back and forth to each other. And I hope we did a lab where you sent one wave and your partner also sent the same wave. And then when they meet, if they're on the same size, they got bigger and then they went through each other. Or like if you sent it on opposite sides, you notice that it canceled each other out in a flat line. And then passed through each other. I don't know. I hope we did a lab like that. Then again, thinking about your class and slinkies, I don't know.
I don't think we did it. I don't remember.
Maybe half of you did and half of you didn't.
I feel like I remember doing it. Well,
maybe one class did and then they effed it up for the other section.
Yeah, that's what happened because that's what they did a lot. One half of the class always got. Yeah, I think I was like.
Okay. So some more pictures here showing electron interference. So the most important evidence of the wave nature of light is obtained by Young, as he was a scientist with this double slit experiment. So what he did is he took light and he had these two slits, and here's a beam of electrons, and they like bent around it, and he got multiple bands, and everyone's like, what's going on here? And it's just an interference pattern. So I do have a kind of a... No, he's just going to talk more about this.
Hey guys, what's up? So I am super into this website right now. It's Generation Genius. And they cover all of the science standards for every state. But what I love about this website is it provides all the resources you need, like straight up. You can print out the lessons. It tells you exactly what's...
Professor Dave here. Let's talk about the double slit experiment.
He knows a lot about the science stuff. Professor Dave explains.
In learning about the first few discoveries that led to the development of quantum mechanics, we discussed wave-particle duality. So we understand that both light and matter behave as both particles and waves. But we glossed over some of the technical details, so let's zoom in for a moment. In 1801, Thomas Young performed experiments where light was passed through a plane with two slits in it, striking a screen beyond. The diffraction and interference patterns that resulted clearly supported the wave model of light, with the brighter bands representing constructive interference and the darker bands representing destructive interference, with the width of the bands being a function of the frequency of the light. Later in the century, Maxwell showed that light is a wave of oscillating electric and magnetic fields. So it seemed as though the case was closed on the declaration of light as waves. But as we said, in 1905, Einstein solved the problem of the photoelectric effect by assigning particle nature to light. Thus, wave-particle duality was born. Later, de Broglie proposed that particles must therefore also display wave-like behavior, and this was shown to be true in an experiment, just like Young's more than 100 years prior. This modern version is what we are typically referring to when we talk about the double-slit experiment. From this, it was shown that a beam of electrons exhibits diffraction and interference patterns, just like light does. This demonstrates the wave-like properties of electrons, and by extension, matter in general. Later, low-intensity experiments showed that even an individual electron, when passing through biprisms or slits, will interfere with itself, making the wave-like nature of the electron undeniable. So it was shown that electrons act as both particles and waves, but not just electrons. Neutrons were also shown to exhibit diffraction patterns. It must be understood that since all particles are also waves, literally any object could hypothetically exhibit a diffraction pattern, so long as the object passes through an aperture roughly the size of the object's wavelength. But remember that massive objects have incredibly tiny wavelengths, so for something like a human being to diffract, they would have to pass through an aperture around 10 to the negative 36 meters wide, which is a trillionth of a trillionth of a trillionth of a meter. So this will be pretty tough, no matter how much you diet. In this way, we begin to see how Newtonian mechanics is not the fundamental descriptor of motion, but rather that it emerges from quantum mechanics as objects become large enough that their wavelengths are negligible. So don't worry, everything you learned in classical physics will still work just fine for any object you can see with your eyes. But along with these waves of matter came the wave function and the quest to describe it mathematically. This would be impossible without the creation of quantum mechanics, which was achieved by a host of brilliant minds. But we will focus on two people in particular, Erwin Schrödinger and Werner Heisenberg. Let's move forward and see what they had to say on the subject. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content.
I really thought he was going to go further into detail.
And you're like, oh no. I'm just kidding.
What's going to happen?
Alright, so if electrons were both particles and waves, then where are they? Can we see them? So, unfortunately, it's impossible to figure out an exact location of an electron due to its velocity or its position. Basically, Werner Heisenberg, which Professor Dave, right, I think his name was going to go on and say, is that he's going to create this principle called the uncertainty principle, where it's impossible to simultaneously determine the position as well as the speed or velocity of an electron in any particle. If you know one, then you are less certain of the other, basically. So any attempt to measure precisely the velocity of any subatomic particle will knock it in an unpredictable way. So, you know, there's no validity to figuring out the position or the velocity of that subatomic particle. If you do know one, you're not going to know the other. Okay, can I move on? Yep, okay. No? Sorry.
So that just tells us that you just can't determine them both at the same time.
Right. But really, you just can't. Because, I mean, like, technically they're like moving at the speed of light. Alright, so Schrdinger developed an equation that treated electrons and atoms as waves, and any solution was known as a wave function. So it also laid this foundation for quantum theory or quantum mechanics, which describes wave properties mathematically for any subatomic particle, electrons, neutrons, and even the subatomic particles of those.
Professor Dave again. Let's take a look at the Schrodinger equation.
He knows a lot about the science stuff. Professor Dave explains.
Through the work of Planck and Einstein, we were forced to accept that energy is quantized, and that
I'm sorry. Why did I do that?
light exhibits wave-particle duality. Then de Broglie extended this duality to include matter as well, meaning that all matter has a wavelength, from a tiny electron to your whole body to a massive star. However, an object's wavelength is inversely proportional to its mass, so objects bigger than a molecule have a wavelength that is so tiny that it is completely negligible. But an electron is incredibly small, so small that its wavelength is indeed relevant, being around the size of an atom. So we must view electrons as both particles and waves from now on. Therefore, we must discuss the wave nature of the electron. So what kind of wave might this be? We can regard an electron in an atom as a standing wave, just like the kind we learned about in classical physics, except that rather than something like a plucked guitar string, an electron is a circular standing wave surrounding the nucleus. If we understand this, it becomes immediately apparent why quantization of energy applies to the electron, because any circular standing wave must have an integer number of wavelengths in order to exist. Given that an increasing number of wavelengths means more energy carried by the wave, we can see the Bohr model for the hydrogen atom begin to emerge as we imagine a standing wave with one wavelength, and then two, and then three, and so forth. This is the reason that an electron in an atom can only inhabit a discrete set of energy levels. The circular standing wave that represents the electron can only have an integer number of wavelengths. When an electron is struck by a photon of a particular energy, this energy is absorbed, promoting the electron to a higher energy state and increasing the number of wavelengths contained within the standing wave. This is why the electron goes to inhabit a higher energy level, and this is what is fundamentally occurring during electron excitation. Furthermore, it is the constructive interference of these standing waves that explains how orbital overlap results in covalent bonding. So we can enjoy a little more clarity in our understanding of chemistry thanks to modern physics. Once it was realized that electrons exhibit wave behavior, the physics community set out to find a mathematical model that could describe this behavior. Erwin Schrödinger achieved this goal in 1925 when he developed his Schrödinger Equation, which incorporated the de Broglie relation. This is a differential equation which utilizes concepts in mathematics that are beyond the scope of this series. But we can certainly discuss the conceptual implications of the equation. Essentially, just as F equals ma applies to Newtonian systems, the Schrödinger equation applies to quantum systems by describing the system's three-dimensional wave function, represented by the Greek letter psi. In this equation, this term is called the Hamiltonian operator, which is a set of mathematical operations that describes all the interactions that are affecting the state of the system, which can be interpreted as the total energy of a particle. But while the Schrödinger equation can calculate the wave function of a system, it does not specifically reveal what the wave function is. Max Born proposed that we interpret the wave function as a probability amplitude, where the square of the magnitude of the wave function describes the probability of an electron existing in a particular location. Looking back at the double slit experiment, we understand the diffraction pattern as illustrating this wave of probability. The pattern is not the electron itself. It is the probability that an electron will arrive at each location on the screen. We can't predict where one electron will go, only the probability that it will arrive at a particular location. If many electrons arrive at the screen, it becomes apparent how their distribution obeys the wave function. So the Schrödinger equation does compute the wave function deterministically. But what the wave function tells us is probabilistic in nature. This idea that nature is probabilistic on the most fundamental level was a lot for the scientific community to handle at the time, and still is for some. So just the way sound waves are mechanical waves, and light waves are oscillations in an electromagnetic field, an electron can be considered a cloud of probability density. There are many such interpretations of quantum mechanics, which involve different ways of viewing the relationship between the wave function, experimental results, and the nature of reality. And there is still no firm consensus as to which view is correct, be it the Copenhagen interpretation, many worlds interpretation, or a number of others. But before you choose a camp, let's keep moving through the development of quantum mechanics, which means we will need to consult Werner Heisenberg. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
That's crazy.
Yeah, so that's why, I mean, that's pretty much the end of the history lesson. Yeah, so I'm done with history. So you can see that it's, they build on top of each other, trying to, describe electrons as both waves and particles, and you're not going to see Professor Dave anymore, sorry. But he was going into how you can't determine the location of an electron, just the probability of where it's going to be. And so this is where it's going to segue into our notes with orbitals. Okay, an orbital is a 3D region around the nucleus that gives us the probability, indicates the this is supposed to be probability, not probably. God damn it. The probability indicates the probability location of an electron. That still doesn't make sense, but it's the probability of where you would find an electron. Okay, so areas that overlap with each other are more dense, and that means you just have a higher probability of finding an electron in that area. Orbitals come in different shapes and sizes. You can see that we have spheres, dumbbell shapes, cloverleaf shapes, rings, and donuts. So S is the sphere shaped. P's are the dumbbell shapes. These are the D's, and then these are the F's. So I'm going to talk a lot about S and P's, and I'm not really going to get to the cloverleafs, which are D's. But yeah.
Wait, I didn't know that we had to write that one thing, the A thing.
Okay. All right. So we're going to get into some crazy vocab terms here. So the first one is quantum numbers. We're going to use quantum numbers to help us describe properties of electrons. It might tell us what type of orbital we're looking at, and then how reactive it is, or which energy level it's in. So quantum numbers specify properties of electrons. And there's a few different types of quantum numbers. The first one is called principal quantum number, and the symbol for it is N. Okay. All the principal quantum number is really telling you is the energy level that that electron is in. It's always positive integers. Electrons with the same N just means that they're in the same electron shell. So energy levels on the periodic table, we have the first row. Hydrogen and helium, you got our second row, that would be N2, N equals 2, N3, all the way down to 7. So which energy level is that electron in? Another quantum number, the angular momentum quantum number, which is abbreviated with that cursive L, which I cannot get to stay in my notebook presentations. It really looks like that. This tells you the shape of the orbital. Is it going to be a sphere shape, a dumbbell shape? Yes. I can be 0 to all pumpers. Okay, so in this diagram, right up here, you can see that these are all orbitals. So here's my 1s, but then I have another sphere. That's 2s. Okay? I see I have these dumbbell shapes. One that goes vertical, and then you have one on the y and the z axes. And they overlap. And so areas that are dense, that you have a very, very high probability of detecting an electron. And then as you go out, it's fewer. There's actually 3 spheres. And you didn't even see this light-colored one because I thought it was part of the picture. So 1s, 2s, 3s. So this sphere just represents that we do have electrons in the 3rd energy level. And in fact, I could hypothesize as to what element this electron diagram is showing me, which element it is. I've completely filled my 1s, so it's not hydrogen or helium. My 2s is lithium and beryllium. These P's, 2p, 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 that fulfills, it gets rid of all these. It's not boron, carbon, nitrogen, oxygen, fluorine, or neon. And then I have a 3s. So it's either sodium or magnesium. So it's kind of cool how you can just look at this and narrow it down as to which element you're looking at.
But will you ever really know which one you are looking at?
When we tell you how many electrons are in each orbital, then you know. Okay. So another diagram just depicting the different energy levels. This would be the first row in the periodic table, second, third, and the fourth. But then it can be, we do have some sub shells or sub levels. So we have 1s. There's no 1p or 1d. 1s is just the first energy level. 2, there are 2 sublevels in the second energy level. 2s, and if you look, Libe, see it says 2s right there. And I don't know if you guys have ever wondered, what do these letters mean? Well, there's 2p right there. So, and Energy level 2 has 2 sublevels. 3 has 3 different sublevels. If we look, it's got 3s, it's got 3p, and then the transition metals tend to screw everything up. Here's 3d. Ooh. Now, I like this diagram because it goes from 3s to 3p, and then you drop down to row number 4, right, where you have potassium and calcium, and then it goes to 3d. So there are some sublevels that have higher energies than others. Oh no, Emily. Is this good?
You went, oh.
Yes, I did. All right, another quantum number. The magnetic quantum number. Wow. It's going to tell us the orientation of that orbit. Is it on the x, the z, or the y axes? Okay, I don't know why these are ones. Hold on, I'm just going to go back a slide. Hold on. Okay. So the magnetic quantum number, all you really need to know is that it just tells you the orientation. That's it. Okay. So is it on the x, the y, or the z? And honestly, I'm not going to if you do have a question on the magnetic quantum number, it will most likely be the definition of that question. Does that make sense? Okay.
Yeah.
All right. So how do we represent orbitals? And I know this is going to get really confusing. Okay. So here I have the different shapes. The S, the P's, the D's, and I'm not even going to touch the, well, sort of. I don't have a picture of the S. But, where's my marker? Okay, each subshell is represented by a dash. Okay, so just for this one S level, I have a dash. And each orbital can hold 2 electrons. And we're going to represent electrons by arrows. Up arrows and down arrows. Okay, so the S level, just 1 dash. If you ever come across a P level, the P level is going to have 3 dashes, or 3 orbitals. So how many electrons could fit in the P sublevel total? If each dash holds 2. 6. Okay. If we look at the D level, how many electrons could it potentially hold? 10, because each one of these dashes holds 2. And then F, 14. I don't think if I do make you do an F, it'll just be 1 element. But the thing I want to point out is, if I have something that looks like this, 1s, 1. You're probably wondering, what the hell does that mean?
S squared.
This 1 is the quantum number, which energy level you're looking at. So when you look at the periodic table, 1s, it's either going to be hydrogen or helium. This S just means it's a sphere shape. We're in the sublevel of S. And then this little exponent tells you how many electrons are floating around in that subshell. So it's hydrogen. So this is one way to show this, but then you could do this as well. That also means hydrogen, just based on its electrons. Does that make sense? In a way? Because the arrow represents an electron. Okay, I'll do another one. Let's do carbon. Okay, so carbon. How many protons are in carbon?
6.
6. Okay, so it's got 6 protons. So we're going to assume that it's neutral. How many electrons?
6.
6 electrons. Okay, so if I wanted to show carbon using the orbitals here, I would always start with 1s. Okay, so you'd go 1s. S can hold how many total electrons? 2. All right, so I have 2 electrons, but hey, I got to get to 6, so I need 4 more. So then what's the next energy level according to the periodic table? So I did 1s, it's gone. Now you're going to do 2s. Okay, you just move on down.
Oh.
2s. So you go, okay,
Wait, did you say you always start with 1s?
always. So now we have 2s. Well, s can hold how many electrons? 2.
Holy cow, you got us tricked.
Yeah, so 2 plus 2 is 4 electrons, but man, we got to get to 6. So now what's the next energy level according to the periodic table? No. Go across.
Wow.
2p. Okay? So you go, okay, we're in the 2p sublevel now. Now it can hold 6. If I write 6 here, 6 plus 2 is 10. I overshot it. We don't want that. We want to get to 6. So how many?
2.
2. So 2 plus 2 plus 2, 6. This is what carbon looks like in electron configuration. If I wanted to show the dash, I'd go 1s, there's my dash. I can hold 2 electrons, an up arrow and a down arrow. And then I'd go 2s, up arrow, down arrow, I'm at 4. And then I'd go 2p. How many dashes are in the p level? 3. And then I'd fill it in. Like that. Yeah, I know. This is...
No, I thought that was a 1 up there. I didn't know that was an arrow. So
Yeah, me either.
I was like, what is she drawing up there?
Oh.
Wait, why didn't you put one after, like...
We're going to get to those rules. We'll get to those rules, Asia.
Is it because we only use one of the dashes for P, which is why we only went up 1? Because,
Yeah.
like, you didn't color in the other 2.
I'm just giving you a little preview of what's to come. I just wanted to see if you guys could catch on just from that information. But don't worry about it. Don't worry about it. It's okay.
That's not going to be on the test.
Oh no, it's going to be on the test.
That is?
Yeah. But we'll have way more practice. Okay.
Okay.
So far, we know this, or at least we think we do. Whoops, at least think we know. Okay. So the arrangement of electrons in an atom. They're arranged in shells. Okay? And the energy level. 1, 2, 3, 4. The rows on the periodic table. We know that there are subshells or sublevels represented by that cursive L. That's the S, the P, the D, and the F. And that they can exist in orbitals. The orientation, is it on the Y, the X, or the Z? So you ready for the last quantum number? Nope. It's okay.
Yeah, I'm coloring.
Yeah.
You gave us notes on that.
Oh, I'm sorry.
It's okay, good.
Oh.
I'm going to feel so bad for Marlene.
I feel bad for Alyssa.
Alyssa's gonna be watching this and she's just gonna hear H go, I feel bad.
I would hate to miss this.
Could you imagine being Marlene, like, laying out the sun and she doesn't even know what's to come?
Is that supposed to be a cursive L, or is that...
Yes, that is supposed to be a cursive L.
She's so relaxed, probably having the time of her life.
I'm gonna cry. Oh my gosh, I did it.
I don't know. She already had messaged me this morning asking if I had posted notes for chapter 4, like the 4.1 notes, and I'm like, we took them on Friday.
She's ready.
And so she was like, oh yeah.
She definitely did not have those.
Or if she does, she don't remember.
Well, she was here Friday.
What?
Oh, Marlene.
We thought she was going to be gone, and then she was here.
And then wasn't that the test? Because she was all peeved because she didn't study for it because she thought she was going to.
No, that was Thursday.
Well, they were both funny to me, so. Riley's just funny. I don't know.
Okay. Can I move on to the fourth quantum number? The spin quantum number. So maybe you saw on 2 slides ago why I had an up arrow and a down arrow. Well, electrons, they spin. They spin counterclockwise and clockwise. And we have to make sure that they're opposites. Okay, so electrons create a magnetic field, and we call them plus half. I can't do this in notebook.
It's like 1/2.
Yeah, but it's just this, guys. It's nothing fancy for this. And this just means up and down. Now I know I make my arrows really weird, and you'll know why when we actually do a whole bunch of these in person.
I kind of like them. I think they're cool.
It's just that when you're going to be drawing so many freaking arrows.
Positive is up and negative is down.
Yeah. You're going to be drawing so many arrows, it just gets super quick when you just do this. Instead of,
I know, I just spent like 10 minutes of my note taking, filling in my arrows from the shells to subshells.
so a single orbital can hold a maximum of 2 electrons, which we did that from the dashes, but the 2 electrons have to have opposite spin states. So as you can see here, an up arrow and a down arrow.
Oh.
And actually, it doesn't really matter. Don't worry about the arrows. I probably just said the wrong thing.
So if it goes down, that means it's spinning a different way than it would if it
Yep.
I'm gonna draw that.
Drops inside.
Sorry.
Oh, stop. Opposite. So fun. There we go.
So down, and then the up arrow goes the other way.
I feel that.
That's me all day.
Okay.
Oh, that's awesome side for us.
Yeah.
Hey, we did it!
Yes, we made it.
Oh, but
9 minutes to spare. Okay, so this is just in summary of what we went through. We went through the principal quantum number, which is the energy level n. The angular momentum, which is the n sublevels, the shapes of it. And then we went to, these are represented the dashes. This tells you how many electrons are in each sublevel. This table's in your book. And I thought it had the 4th one, but maybe I'm not seeing it. No. So, in summary, 4 quantum numbers to describe an electron, properties in its orbitals. Here's the principal, the angular, the shape of it, the magnetic, which is the orientation of it, and then the spin, up arrow versus down arrow. So this slide's, I think, probably a nice little summary of everything we just went through. So, whew. So tomorrow you'll have a 4.2 worksheet, and then we're going to take everything we just learned today and utilize it. We'll do the dashes and the arrows on Friday. So tomorrow's a work day, and Mr. B is your sub.
Oh god.
Mr. B.
He's gonna talk the whole time.
What's the color?
I thought you said Mr.
Shh, I'm still recording.